All right. And so, there definitely seems to be some kind of relationship. We want to create a model, okay? And um, and so, we can create a linear model, okay? So a basic linear model we can just do by doing lm. lm.fit is often what we call the kind of the fit that we create with our linear model. And we would do something like using the function lm, and we would do mpg as explained by horsepower. And we would do data equals auto. And this would be kind of our initial fit, and then if we wanted to add this, we can do something like AB line lm.fit, and maybe we'll do color equals blue. Okay, and this is your linear model plot to fit a straight line to the relationship. And we would say, maybe that's not the best fit here, right? Just eyeballing. Okay, so we could fit other. We'll just play around with different polynomial fit, right? So we can say, okay, what if I took horsepower and I kept horsepower as it is, but I also created a column called horsepower squared, okay? And we can do a quadratic fit, right? And so you can do lm.fit2, and this would be lm mpg as explained by horsepower, and then plus, I forgot the command. Yeah, today I just used poly, but let me just back up. Yeah, I horsepower squared. Okay, we'll do I horsepower squared, and data is equal to auto. Okay, and then I don't think I can. I forget how to plot the line there, but that would be another way. Okay, or another way is you can do lm fit is you can just do lm mpg as explained by and you do poly on horsepower, and poly kind of creates what they call orthogonal polynomials. It's basically doing the same line there, but the values end up being just ever so slightly different. But you're fitting another quadratic fit here. So let's just take a look at summary of lm.fit2, and we'll do summary of lm.fit2a. Okay, and we're getting kind of your adjusted R squared of 0.687. Yeah, right there around the same thing. Okay, so we're getting some fits, and we can kind of just try these out. And there's a question is, okay, what if I want to third order polynomials or fourth order polynomials? What is going to model our data the best? Okay, and so to kind of answer this question, we can try this out by splitting our data into kind of our training set and a test set, or in this case we call it a training set and a validation set. Okay, so the first method is kind of the validation set method. And we take our data and then some of the rows go into kind of your train. You just randomly select rows, and then the other rows get randomly selected and they get thrown into the test set or the validation set. and that's it. Okay, and so this process here is generally what you do is you just use the R code sample. You'd say sample, and then however many rows that you have, you do kind of your number of rows of your data, and then basically your training size. And then you would store this output. This you would store as kind of the indices of the train, okay? And so what you would do is you would subset your data based on the indices. This goes into kind of your train set, and then I should do it this way. And then the test set basically becomes, you subset the data for everything but those indices. Okay, becomes your test set. And then you go through the process. Yes, question?
How did you know what size you wanted to use of train versus test?
Yeah, it's a little bit arbitrary. Okay, at least you have different opinions on how big this should be, and this is probably not may not be the best way to go. Okay, so we'll do this. Okay, but the big disadvantage here. Something's wrong with my thing. I don't know what's going on. Okay. The disadvantage is that your training data set is missing everything that's put in the validation set, right? So if you decided to do a 60-40 split, you're training only on 60% of the data, okay? Or, if you do a 90-10 split, that 10% that you're using to test, depending on which 10% ends up there, your estimate of the error could be wildly too big or too small, because there's now that which 10% of the rows get selected for the test data set, now that's important. Okay, so disadvantage is you're either missing lots of data in the training, okay, or a lot depends on the rows that go into your validation set. Okay, but let's not worry about that right now. Let's just see what this looks like when we do it in R. Okay, so I'm going to get rid of these models that we made. We'll just remove lm.fit and remove lmfit2 and remove lmfit2a. Okay, so we'll get rid of those, and then we'll so what we're going to do is we're going to sample. There's a total of 392 rows in our automotive data set. We are going to select 196 out of the 392. So we're doing a 50-50 split. Okay, so we're just taking 196 out of the thing, and that's going to be our train data. Okay, so with train, these are the 196 rows that we will select. Okay, and so this is just totally shuffled. And then we're going to create a fit. We're going to do lm.fit, and we just do MPG based on horsepower, we'll say data is auto except, and we say, however, fit your data just on this subset using train, using these indices to choose the data that we use to fit our data. So okay, so maybe if I add a comment, it would be fit or predict, create a model to predict MPG based on horsepower. Use the data auto, but only use the rows that are defined in the vector train. Okay. So we do that, and okay. Now we can take a look at this fit. We can say lm.fit, and we can see this is kind of the estimates that it has produced. That's the intercept, and that's the slope. And what we can do is we can use this to make predictions, okay? And so R has a function called predict. What you give it is you give it the model that you just produced, and then you give it the data that you want to have it make predictions for, okay? And so in this case, we're just going to have it make predictions for all the data, okay? Except, and then, so if I just run this, predict on lm fit auto, it's going to produce predictions for all 300, I guess, wait, 97. It should only be 392. I think the row numbers are just named funny. But let me just do length here. Yeah, so it makes predictions for all 392 rows. And all we're doing is we're going to just say, get rid of the ones that were used in the training data set. Okay, so that's what this is. The bracket subset, we're subsetting minus train. Minus means I don't want the ones that were in the training data. Okay, and so I do that. So these are the predictions that I made from for our test data case. Okay, so these are the predictions, test underscore predict, and we have the actual values. We can just take from auto, we can just take that column MPG and get rid of the values for the train. We can just say, oops, get what are the values? Okay, here we have 196 values. Okay, so these are the actual values that we have. So we can compare our predicted values versus what they actually were, right? So row named 397, we predicted 27. The actual value is 31. Row named 395, we predicted 26.75, and the actual value was 32. Okay, and if we want the mean squared error, is we just take the difference between the actual and the predicted, we square that difference, and we take the mean. Okay, so the mean squared error between, for this model, between the training and the validation set, we have a mean squared error of 26.14. It's not hard to just duplicate this code, but this time putting in a different polynomial, okay? So now we're gonna fit a model of polynomial degree 2, okay? So same exact command, lmfit2, this time predict mileage based on a polynomial of horsepower degree 2 using the same training subset rows. We're going to create our predictions using the function predict. We remove the training rows, so we just have the predictions for the test rows. And then we're going to compare the actual test values to the predicted test value, or predicted values. And then we square that difference and we take the mean. Okay, mean squared error there. Same thing, this time I'm doing a polynomial fit of degree 3. So with a linear fit, my mean squared error between the training and the test data is 26.14. With a quadratic fit, the difference between the test and the training and test or validation set mean squared error is 19.82 and 19.78. So we see a big drop between 26 to 19.8. Not too much of a drop between 19.82 and 19.78. Right. So that's what we see here. Okay. But then there's the question of, well, what if I had a different training set and a different test set, right? I selected my rows for the training set by doing sample 392, 196. What if I had selected different rows, okay? And so we're going to just try, how does this differ? I do set seed.to, and then and we do run basically the same code. And so now my values are different. Instead of 26 and 19.8 and 19.78, I have 23.3, 18.9, and 19.25. Okay, so the values are different based on what data rows went into my training set and what went into my test set. Okay, and so kind of the natural extension was, what if we did a whole bunch of these things and just kind of average the results and kind of get an idea of which model is best, okay? And so that's kind of the setup. We start off with this kind of validation set. We just split the data. In the beginning, we just split it in half, or you might pick a different fit, okay? And so now we have cross-validation methods, okay? So leave out one cross-validation, or leave one out cross-validation. Basically what it does is it says, okay, you originally have 392 data points, okay? We're going to create a training set with 391 and a test set of just one value, okay? And so you fit your model based on those 391, and then based on that model, you make your prediction for that one missing value. You get an error metric right there, okay? Except you don't want to base it just on one, so you do it for every single data point. So you have to do this process 392 times. You do it for, the first data point, you leave that one out, you use the other 391. Then you leave the second data point out, and you do on the other 391. Okay, each time using the 391, you create a training data set, and then you create a model. You use that model to make a prediction for that one missing value. You calculate the error, and you do this 392 times, or one for every single observation. Then you average all of those errors across all 392. And that's the leave one out cross-validation for that one model. Then you try another candidate model. You say, okay, here's model 2. We're going to do the same thing. I leave one out, train the model, make a prediction. Then I go to data point 2, leave that one out, train the model, make a prediction. You do that all 392 times, and you average all of those, and now you have a cross-validation error for model 2. And you do this across all of your models, okay? And then at the end, you say, okay, what was the cross-validation error rate for model 1? What's the cross-validation error rate for model 2? And based on that, you kind of have an idea of which model produces the lowest cross-validation error. Okay, so I'll draw the picture, and okay, so you do train, validation, and then again, you feed this into your, so this is the validation set. You feed this into your model, and then you get an error, right? Okay. Leave one out. Cross-validation is, okay, so basically everything goes into your train, whoops. Train is all but one. Okay, and then one observation. Your test is one observation. I shouldn't even draw it like that. I should just do it like this, okay? Use this to train your model. Okay. And then you feed this into your model to get a prediction. Prediction, you compare to the actual value. Calculate an error. And then you do this for all repeats for all rows in the data. And then repeat for all models. Okay, so there is a nice little function here. Maybe I'll do the manual one first. Okay, because maybe I can explain the manual one, and then there's a nice little function that does it for us. Okay, so if I look at the dimensions of auto, there's 392 rows, okay? And then, well, 9 columns, but. So the errors, I'm gonna create a matrix. I'm gonna test out 5 models, okay? We're gonna start off with, basically I'm gonna do fit polynomials from order 1 to 5. So linear up to 5th order polynomial, okay? So my errors, I got 392 times 5, okay? So this is, I've got a matrix. I'm gonna just fill this out with zeros in the beginning. Okay, and what I'm gonna do in the beginning is, I'm gonna do 1 through 392. So I've split the data into test. Test is gonna be whatever k is. So the first time it runs, it's going to be row 1. The second time, it's going to be row 2. The training will be everything but row k. Okay, that's going to be my training data set. Then I fit, then I have another loop here, okay? The inner loop says fit, create a linear model fit, where you fit MPG based on a polynomial of order I. So the I is going to go from 1 through 5. Okay, so we start off with polynomial of order 1 through 5. Okay, the data you're going to use to fit your data is going to be the training data, which is basically everything in the auto except row k. And then you're going to calculate the error, which is going to be the difference between your test MPG, which is basically just that one row MPG, minus the prediction for that one observation. You square that observation and store that error into row k, column I. Okay, and so when we first do it, we're going to do it for row 1 is our test data, and then we fit order 1, order 2, order 3, order 4, order 5 polynomials. Okay, once we do that, then we'll go to row 2, fit order 1, order 2, order 3, order 4, order 5, and then we do that all the way down to row 392, order 1 through 5, okay? So it takes the computer a little bit of time to run this, okay, because it's got a lot of things to do. And then at the very end, we're going to just take the mean of column 1, which is going to be the leave one out cross-validation error of model 1, the linear fit. Then we take the mean of column 2, cross-validation error for models of order 2, and so on. Okay, so I run this. It's running. Okay, and it's done. All right, so this is the cross-validation for the linear fit, 24.23, and then it drops down when we fit a quadratic polynomial. It drops down to 19.24, 19.33, 19.42. So after we go from a linear fit to a quadratic fit, we see a drop, but then not too much change after that. Okay. All right. Does this make sense? This leave one out cross-validation and the manual implementation and the loops that I've built inside each other.
the 9 dimension.
The what dimension?
392 by
392. Oh, the 9 here says in our auto data set, there are 9 columns. We're only interested in 2, the miles per gallon and the horsepower column. But there were other ones like, I don't remember, weight and the name of the vehicle. And yeah. So this has nothing to do. This has nothing to do with it. Okay. And then there is, R has a function called cv.glm, cross-validation for generalized linear models. Generalized linear models, if you don't specify over here, if you don't change the family of the generalized linear model, then it's just a linear model, okay? But you can change the family, and that's why it's GLM. And this thing only works for generalized linear model fits. So anyway, so we basically do GLM, you can, for today, we can pretend that this is the same thing as LM, okay? It's just that the output is a little bit different. So we're fitting a linear model between miles per gallon and horsepower, going from 1 through 5. So polynomials of order 1 through 5 using data auto. Okay, so this does it, and then we do glm.fit, and then cross-validation.glm does all of this work for us. Okay, and this is a tool that exists inside library boot for Bootstrap. Okay, so we run that. Takes a little bit of time to run. Okay, and the values that this produces are exactly what we got. Okay, yes?
Does the cv.glm function return a data frame? Is that why you're indexing to column delta row 1? Or?
Yes.
Okay.
Yeah, it actually returns a list of a bunch of stuff. I forget everything that's in there.
Is delta a method of the function?
Let's see, cv.glm. Okay, let's just see. Cross-validation for generalized linear models. Let's see. Okay, so the value that it returns, okay. The k using k-fold cross-validation. We'll talk about that in a second. Delta is a vector of length 2. The first component is the raw cross-validation estimate of prediction error, and the second component is the adjusted cross-validation estimate. I forget how the adjustment works. It says the adjustment is designed to compensate for bias introduced by not using leave one out cross-validation. Oh yeah, I forget. But yeah, there is like a adjusted. But basically, the output of cv.glm, it is a list, but there's really only one thing that's interesting to us, which is delta. Call is the original call. The k is k. If you did k-fold cross-validation, which we'll talk about next, versus leave one out, and then the seed is the value of the random seed when GLM was called. These are useful in case you want to use the output of cross-validation GLM in another function. Otherwise, in terms of just for us to, what's useful to us is this row delta, okay, in the first value there. Yes, John.
I might be a little confused, so my question is kind of weird. But so I'm just trying to like reconcile this with the first validation thing where you did a train test split and you compared the mean square error.
Yeah.
So you did a train test split there, and you have like these, you have whatever the mean square error calculated in that sort of example.
Yes.
We're looking at this other, I guess what was the cross validation?
Yeah.
It went out. Are you running that against the whole sample? Is there no, like, is there a need to do a training test split there, or is it?
Yeah, I am doing a training test split. The training test split for leave one out cross validation is that the test case or the test split is just one row. You're using the other 391 rows as your training data, and then
I see.
And then you're using just one row as your test. Okay, but because the problem with if you did this only one time, then your evaluation of what is a good or bad model depends very much on what row happened to get selected for the test case. So to eliminate that, we're going to let every data point have an opportunity to be the test case. Okay, so leave one out, cross-validation. We go through all of them. We do 391 versus 1 and so on. And we do this for the whole thing. Yeah?
You in theory do this with like a 90-10 split or?
Yes, that's exactly what k-fold cross-validation is. Okay? So yeah, if you feel like this is a lot of work, okay? I mean, it's not. You just have the computer do it. But if you there's other reasons. There's this Biasvariance trade-off, okay? So if you don't want to leave one out cross-validation, yeah, the next option is to do k-fold cross-validation. So k-fold, we often do 10-fold or 5-fold cross-validation. And so 10-fold cross-validation splits the data into a 90-10 split, okay? And you just split the data into 10 non-overlapping sections, okay? So you get 10 non-overlapping chunks, and then and you use the other 90. So the first chunk gets selected as the test case. You use the other 90% as your training case, okay? And then you fit a model to that thing, and then you calculate, and then you make predictions on the test case. You compare the predictions to the actuals to get some error measurement, okay? And you do that for all 10 cases for that first model. Then you go on to the second model, okay? Second model, 90-10 split. The first one, you train on the 90%, you test it on the 10%. Then you go to this, then you use the second test case, train on the other 90%, test on that first 10%, okay? So, so I have kind of a manual implementation here. My values will not match up exactly with the one because of when you do the split between the 90 and 10, it's random, right? So here the manual implementation. Let's see, and I know it's kind of starting after it outputs has the output for CVD error 10. It says set.c17 there. This is what I've done. Okay, so to do this, I'm going to do a sample 392. This just takes the rows for the 392. It shuffles those all up. Okay. I'm going to create a matrix called errors to store all of my outputs. And then now my outer loop is for k in 1 through 10. Rather than k in 1 through 392, now I only have 10 test data sets. Okay, and then so my from and to will start off at 1, and I'm basically, I said, okay, there's 392, so I'm going to go 1 through 39 for the first one, then 40 through 78 for the second one, and then 79 through whatever for the last one. So I'm only going to get to 390. I'm not going to get to include those last 2 data points. I mean, they'll always be in the training set, just those last 2 data points never actually get to be in any test set, okay? And, people have different perhaps methods in terms of how that goes when you have, a number of observations that's not an even multiple of 10 or something, right? Or of your k. Okay, so anyway, rather than just doing the first 39 goes into the test and then the next 39 goes into the test, I've shuffled them up, okay? So in SAMP, which is, I'm going to take take SAMP here, which is the 392 rows, and I'm going to do the first 39 in this vector to be my test case, and then the next 39 to be the next test set. Okay, does that make sense? Okay, and so just like before, I've split my data into a testing set and a training set. Okay, I fit my data on the training set. I use the training set to create predictions, and I compare those predictions to the actual values on the test set. Okay, and then in this case, I'm going to square those and take the mean, and I get so I'm going to get 10 values here for each thing. So we're fitting polynomials of order 1 through 10 in this case. That's just what the textbook did. So I did something accordingly. Okay, and then after that, I take the mean of the 10 different kind of test data sets. Okay, so when I run this, I get values like 24.239, 19.368, and so on and so forth. Again, this is implemented in R nicely. You know, I write the manual code for you to kind of study and get an idea of what's happening under the hood. In practice, you would not really implement leave one out cross-validation manually or k-fold cross-validation manually. I mean, you could, and there's nothing wrong with it. But in practice, we generally use the built-in tools. But I wanted to give you kind of a peek inside the black box of what's happening, rather than it being totally opaque. At least you have some code if you're willing to kind of sit and parse through it to get an idea of exactly what's happening. Okay, but because it's I'm not entirely sure how the cross-validation errors get selected. My cross-validation errors do differ a little bit from the cross-validation errors that were selected, that are calculated over here. But they are, quite similar to each other. They're off by, it looks like, less than 1 percentage point. So, so that's that's good, right? Okay, and what we see is that these are the total cross-validation error estimates for the different models that we fit, right? We fit a linear model, a quadratic, cubic, and then order 4, order 5, order 6, so on up to order 10. And what we see in all of these cases is that there is a significant drop in the cross-validation error going from a linear to a quadratic fit, but then there's not much improvement after that. So we would probably go and say we should just go with the quadratic fit rather than making a model that's much more complicated. Okay, and this was just a very simple example using regression, but the ideas of cross-validation apply for many other data sets in that, or other types of modeling, in that a lot of times you have a training set, or you want to take the data you have and split it into a training set and a test set to get an idea. Okay, and in fact, if you go on Kaggle for a data science competition, or if you do enter a data science competition, oftentimes what they have is they've got a big data set and they've split it into a training set and a testing set, except they keep that testing set hidden from you. Okay, so you get your thing, which is what they consider to kind of the competition data set, and then you probably should split it into training and testing sets for yourself, so you can come up with a model to then submit against their secret hidden test set that you never got to see, right? Because if you know all the answers, it's easy to come up with a model that's going to give you the answers. The question is, if you don't know the answers, can you create a model that will still hold? And that's what cross-validation, the point of all of this is about. I mentioned something kind of, so this was leave one out cross-validation, and then and k-fold is basically, you're going to split this into kind of k pieces, right? And basically, you know, each chunk serves as the test set. We have, yeah, there is something called the bias variance trade-off, and the idea there is that when you leave one out, cross-validation, you're going to kind of overestimate the your variance is going to be a lot larger, I think. Let me just review this. Okay, yeah. All right, so I'm just going to read from the textbook that says, it turns out that leave one out cross-validation has higher variance than does k-fold cross-validation, you know, where k is less than n, which is, you know, every scenario, okay? So this is page 183 in Introduction to Statistical Learning, okay? And why is this the case? When we perform leave one out cross-validation, we are in effect averaging the outputs of n, in this case 392 different fitted models, each of which is trained on pretty much identical sets of observations, right? Only one observation changes from set to set, okay? Therefore, these outputs are very highly correlated with each other. In contrast, when we perform k-fold cross-validation, where k is something like 10, we are averaging the outputs of only 10 fitted models that are somewhat less correlated with each other, since the overlap between the training sets in each model is smaller. Okay, so in the other cases, you basically had 390 observations overlapping, and then when you have 10-fold cross-validation, you know, you have whatever, only about 80%, okay, of the values overlap, okay? And so since the mean of many highly correlated quantities will have a higher variance than does the mean of many quantities that are not highly correlated, the test error estimate from leave one out cross-validation tends to have higher variance than the test error estimate resulting from k-fold cross-validation. Okay, so it's the problem of the training data set that you're using is there's so much overlap between different test sets when you're doing leave one out cross-validation versus k-fold cross-validation. There's still a lot of overlap, but significantly less. And because of that, your estimate of the variance is much, the variance of your estimate is much lower for k-fold cross-validation, okay? And oftentimes we use k equal to 5 or k equal to 10 because, I don't know, those are generally good numbers, but, you know, there's no rule against having things that are much bigger or smaller. Okay, so that covers cross-validation, okay? And I apologize I didn't write a whole bunch of text here, but I do feel like the text in the textbook that covers cross-validation is very good, okay? That covers it at a accessible yet still thorough enough level that you have an idea, you understand what it is, and it's not just pure black box method, okay? It's chapter 5 in the thing, and that explanation of leave one out versus k-fold is on page 193. Okay. Or something like that. Okay. and yeah, this code also kind of works how the cross-validation stuff works. I did not do the same for the Bootstrap, although I can write some code that will kind of give you a peek inside the black box of Bootstrap. Okay, so the last resampling method that we will cover today is going to be Bootstrap. And I don't know if you guys have heard of Bootstrap or exactly know its purpose, but well, the name comes from the idea of kind of pulling yourself up by your bootstraps, which that's like an old adage, and I don't know what I was trying to figure out where that phrase even came from in the first place, and a funny story I came across, and this may or may not be the truth because you can't trust the internet, but was that apparently some German folk tale was that that the hero got stuck in a bog, and he got stuck, and he said, well, I'm going to get myself out, and he just pulled himself up by his bootstraps and got out of the bog, which of course doesn't make sense, but if you're a German folk hero, it does. If you with Bootstrap is we are trying to get estimates about the population based on one sample and only one sample. Okay, so usually, like, we talk about the sampling distribution, right? The sampling distribution. Did I simulate it last week or not? Or I talked about the idea of repeatedly drawing random samples from the population, right? I can't keep this straight. Okay, but the sampling distribution is the distribution of all the possible values of a certain sample statistic, right? So you take, if you're taking samples of size 10 and you calculate X bar, the sampling distribution is what are all the different possible X bars that you can get if you repeatedly take random samples of size 10 from the population. With Bootstrap, we don't know what the population is, right? So, what is going on here? Okay, so we'll do Bootstrap. Okay, we only have one sample. Okay, and we do not know what the population looks like. So I'm just right over here. Okay, sampling distribution if the population is available. We would take the population, okay, and we're going to just take a little piece out. This is our sample 1. And from sample 1, we calculate X bar 1, okay? Then we take another sample, we do sample 2, and we get X bar 2. And then we come and we get sample 3, and we repeat this, and we can do this over and over if the population is available to us, right? And we can just do this thousands of times. Thousands of X bars. And we can get a distribution. This is the sampling distribution of all the different possible X bars. Or this would be an estimate of the sampling distribution. This is kind of estimated sampling distribution of all the possible X bars. Okay, so that's, this is where the central limit theorem comes from, okay? But this is the sampling distribution, okay? And the central limit theorem says, well, so this is the idea for the sampling distribution, and the central limit theorem just says that this sampling distribution is going to look like the normal distribution. That's what the central limit theorem says. Okay, so this is nice if we have access to the population. Bootstrap, we do not have access to the population. What do? Okay, well, we just say, you know what? I'm going to pretend, I'm going to take my sample. This is my sample. This is my sample. And you know what? I'm going to multiply it by infinity. Okay? I'm going to just create infinite duplicates of my sample. I'm going to make a very strong assumption here, which is my sample was randomly drawn from the population. Therefore, my sample, it's not a huge stretch to say my sample is representative of the population. That's what we're going to say. Okay, that's the biggest assumption we're making in Bootstrap. We're going to say my sample is representative of the population. That's what we're going to say. So what does that mean? That means I can just make 1,000,000 copies or an infinite number of copies of my sample. Okay, so we make what's going on with my thing? Okay, an infinite number of copies of my sample. And then I say, ta-da, now I have a population. That's what I'm doing, okay? I'm just take my sample, I make an infinite number of copies of it. Look at that, this is my, your poor man's population is what it is, okay? And then I want a sampling distribution. All right, let's do it. We're gonna take a sample, get x bar 1, we take another sample, x bar 2, take another sample, x bar 3. Do this over and over and over and over again, and now I have an estimate of the sampling distribution. Does that make sense? Okay, that's effectively what we do in Bootstrap. We just say, you know what, the sample I have is representative of the population, so I can make infinite copies of it. And now I have my quote-unquote population. And then, now that I have my quote-unquote population, I can generate a sampling distribution kind of like the way I did before. I would just draw a random sample from it, calculate an x bar, or whatever statistic it is, and then we get a sampling distribution, okay? The thing is this sampling distribution is going to be strongly biased by whatever our original sample is, okay? So this thing is going to be really terrible at giving estimates of what things like the mean is. But it could be useful in giving us an estimate of what the standard error is, okay? So this will be bad at giving an estimate of the mean, but pretty good at giving an estimate of the standard error, unless our sample is really crazy and not representative of the population. Again, this is kind of the heroic assumption that we're making here. Okay, so this will be bad for estimates of the mean. Good for estimates of standard error. I'm going to just write SE.
Why is that true?
And good is even risky to say. The bias for the mean is a lot more influenced by the bias of whatever sample that we get than the standard error is. So the standard, as long as our sample is kind of representative of the population in terms of the amount of spread we get. Okay? All right. At a practical level, we don't actually have to make infinite copies of the sample and then draw samples. Okay? We don't have to make infinite copies. All we do is we say, I'm going to just sample with replacement. Because sampling with replacement is effectively saying, I've got infinite copies of my sample, right? So at a practical level, we don't really make infinite copies. We're just sampling with replacement, okay? And that's what we do with Bootstrap, okay? So Bootstrap, okay, we don't actually make infinite copies of our sample. We just resample our sample with replacement. And that is effectively making infinite copies of your sample. Okay, and so we'll take a look at the example in our textbook. Okay, the example in our textbook, starts off maybe more complicated than it needs to be, but sure, it's okay. So we're looking at we're going to start off with some data. The data we're looking at is called portfolio. Okay, and in portfolio we've got a bunch of X and Y values, right? And these are this is some fictitious data set, okay? And what we're doing is we're going to try to figure out how much to invest in investment X and investment Y. Let me see, where's the and how the amount we can invest in one over the other is let's go. Okay, so it says, suppose that we wish to invest a fixed sum of money into two assets that return yields of X and Y. Okay, so I guess investment 1 and investment 2, but investment 1 can, perhaps it takes a loss of negative 0.89, and or maybe it gives us a return of 1.04. Okay, so we want to know, try to figure out how much we should invest. And so anyway, it says one can show that the value that minimizes the risk is given by some formula. All right, and that is the value that we are trying to calculate. So this is the sample statistic that we are calculating. Variance of Y minus the covariance between X and Y divided by the variance of X plus the variance of Y minus 2 times the covariance. Okay, whatever. This is just the statistic that we are trying to calculate. And currently, oops. So yeah, portfolio. Okay, so then okay, so currently my current estimate of this value is 0.5758. Okay, so this I can use to help guide me in terms of how much I should invest. Now, into each of these options here. So this is the details of this is not as important, okay? This is just the sample statistic that we are interested in calculating. The example I drew on the board was we were calculating the sample mean, but it could be something else. Maybe it's the covariance that you're interested, or the median, or whatever it is, okay? You're calculating some kind of statistic. In this case, it's like a complicated value, but we just want to know what this is, okay? This number is based on the 100 random observations that I happen to have in my sample of data, okay? Now, if someone else had a different set of 100 observations, they might have a different value that they would get, okay? And so what we are curious in is how much does this thing vary from, could this vary from, one person's observation of 100 data points and someone else's observation of 100 data points, okay? So to do this, I can run maybe I'll do some manual. I'll do a manual and I'll post this code. Is we can just start off by taking a random sample, and all we're going to do is we're going to sample portfolio 100 times, but replace is true, okay? No, this is not what I want. Sample. Oh, okay. No, this is how I have to do it. So I'm going to do sample. So there's 100 rows in portfolio. I want 100, I want a value of 100, and I want replace equals true, okay? So random samp, this is 100 rows selected from, that I'm going to select from portfolio, but this is with replacement, okay? Meaning that I can select the same row more than once, and some rows might not get selected at all. Okay, so this is my random sample that I'm going to use. And then I'm going to say, from portfolio, I'm going to subset this, and I want the rows that are specified by this vector random sample. Okay, so this is going to be kind of my random portfolio. And so here's my random portfolio, and then based on this, I want to calculate this sample statistic. Okay, so after one iteration, or just one running of this, my sample statistic takes on a value of 0.575. Oh, no, I messed something up here. Oh, X and Y. No, that's exactly the same with what I had. Let's random portfolio $y and then X. So we're going to pick the appropriate X and appropriate Y. Okay. So I select my 100 random rows with replacement. I subset portfolio based on those 100 random rows. I'll subset Y and X accordingly, and then I calculate my sample statistic. Okay. So in the original data set using all 100 rows, my sample statistic has a value of 0.5758. After sampling another 100 rows with replacement, which is effectively taking a sample of size 100 from my infinitely duplicated population, I have a sample statistic of 0.596. Okay? And if I did this again, okay, and I ask what is my sample stat this time, now I get 0.5796, okay? So each time we're getting something similar, but also a little bit different, okay? This time we got something significantly smaller of 0.494, right? And so we can repeat this many times and get an idea of the sampling distribution of all of these sample statistics, okay? So in the manual way, I would create a vector of 10,000, and then I'll just do a for loop for I in 1 through 10,000 and throw all of this in here. Okay, and this would be, so we would take our sample stats in slot I, we would take the sample stat that we calculated. Okay. So I would do this. We would let this run 10,000 times. Okay. Each time calculating something a little bit different. And then we can create a histogram of our sample stats. Okay. And so we see most of the time it's right around our observed thing, but we see sometimes we get values slower and values greater, and we can get a standard deviation of this, sample stats. Okay, and you know, this is an estimate of kind of its standard error of this thing. Okay, what do we, with R, we can use its built-in boot function, okay? Using the boot function, you have to create something for the statistic that you're looking for. In this case, the statistic we're calling is alpha.fn, and it's a function of two variables. It's almost all the functions that you use in, or two arguments, all the functions that you use for bootstrapping, the function takes in a data argument and an index argument, okay? And all you do is you subset the data based on the index, and then you calculate your thing, okay? And so in this case, on the original data, when we run it, we get exactly what we calculated ourselves, okay? And then to run Bootstrap, you run boot, and then you say alpha.fn, the function, and you say repeat this 1,000 times, or maybe I'll do, you know, we can do 10,000 times or something like that, okay? So it runs, and then, and this is the estimate of the standard error after 10,000 replications, which I think was pretty close to the estimate that we produced of our standard error, right? So we did this 10,000 times. This is our estimate of our standard error, 0.0914, and you know, this I think shows exactly what we're doing, but you can use the boot library function to do this same thing, okay? And Bootstrap, again, the big idea is we don't know what the population is. We want to estimate kind of some properties of the sampling distribution. How can we get an idea of what the sampling distribution is? We just say, we make a very strong assumption that says the sample that I have is representative of the population. Therefore, if I made infinite copies of this thing, then I have a pseudo population, okay? And effectively, on a practical level, that means we just resample our sample with replacement. And if we do this repeatedly many times, we can produce a sampling distribution ourselves and get an idea of what the sampling distribution looks like, okay? And so the Bootstrap can be used in you know, estimating that standard error. That's probably its most common thing. But there is an example that uses it to kind of get estimates of the standard error for you know, a linear model. So they go back and they take a look at that automobile data set where they're fitting miles per gallon based on horsepower. and you get estimates of the standard error that way as well. Are there questions on this? On Bootstrap? Feeling okay? Okay. We end at 8:50 or something like that. We're 8 minutes early. I think we can call it a night. And so we'll end here. And then yeah, I'll be sure to post kind of the manual Bootstrap code up on our not R, on CCLE for you guys to take a look at. And then I'm still writing a homework assignment for you guys, so so be on the lookout for that. And yeah, have a great week. We'll see you guys next Monday.